Let's look at the features of the Michaelis-Menten equation. And the way this would be set up is we would call this a steady state enzyme experiment. We would have various substrate concentrations with the same amount of enzyme. We would monitor those reactions, so we would know what the substrate concentrations are. And we would be able to somehow or another look at the reaction velocity, the initial velocity. And then we plot the velocities, those initial velocities, as a function of the substrate concentration. And so that would look like this. So here we've got the initial velocity as a function of the substrate concentration. Now what we expect, of course, if you have no substrate, that you're not going to have a reaction. So there should be a point that is at the origin like this. But as we add substrate, we will see the following trend. So we'll have an experiment that has some substrate and some velocity that corresponds with that. We'll do, say, another experiment that has more substrate than that even, and maybe the plot was like this. And then we'll increase the substrate concentration again. Maybe we get this velocity, and we'll keep doing the same thing. And so we'll have this one. Notice what happens is that it levels off, and it produces that familiar shape we've seen before called a rectangular hyperbola. So the Michaelis-Menten equation on the previous page is a rectangular hyperbola, just like we saw with the simple ligand binding case, because something similar is happening. We are looking at enzyme activity, in this case velocity, instead of binding occupancy, as a function of substrate or ligand concentration. And so it makes sense that at zero nothing should be happening, and at high enough substrate concentration there's going to be no change in the reaction rate because we've saturated the enzyme fully. And so I can try to draw a line through these points to kind of illustrate that rectangular hyperbola, and we can see how it saturates and flattens out. Notice that we can, just like before, we can kind of trace this back to the y-axis, and before we called this 100% saturation, but this is no longer about binding only. This is the velocity that's maximal for this reaction. So we call this Vmax, right? So that was that parameter that we saw in the equation. Now remember what we did before so many times is we look at something, when we have a curve like this, we often will go down to the 50% mark, right? So this is Vmax divided by 2 right here. And we will trace that over to the plot, and we will drop a line down to the x-axis. Well, guess what? This is the value known as Km, that collection of rate constants that we saw during the derivation. So the whole point of this, the whole point of steady state kinetics at its core, is that we're going to carry out a reaction at various substrate concentrations, measure the velocity, and we will, from this plot, be able to extract the Vmax and then the Km that will tell us various things about the enzyme. What are those things? Well, the Vmax is the maximal velocity of the enzymatic reaction when we're saturating, so way out to the right-hand side of those plots. Essentially, we're saying that all of the enzyme is in the form of the enzyme substrate complex. So that's what we say when we say Vmax. It is indeed a velocity. It's a type of initial velocity, and so it has units of molar per second. And it's certainly true that if Vmax is a large value, it's going to be that indicates a faster reaction. Well, major thing I want to point out is that Vmax is a property of the experiment. And what I mean by that is if you change the amount of enzyme, you alter Vmax. It's not an inherent property of the enzyme. So for example, if I have initial velocity as a function of substrate concentration, and let's say I have one that looks like this, and we're going to say that the total enzyme concentration for that plot equals 1, whatever that 1 happens to be. I'm not worried about the units. Well, if I double that, so let's say we double, for this reaction, the enzyme total equals 2. Well, guess what? This Vmax here, and now this Vmax here, is essentially half as much. So it takes 2 of those to equal one of the other ones, right? Now kcat, however, is a rate constant. And it's all about how effective an enzyme is at catalyzing the reaction, how good it is at the chemistry. Larger K, larger rate constants indicate a faster reaction. Now, an important thing about kcat is it's a property of the enzyme, not the experiment itself, because it's independent of the enzyme concentration. And so we can calculate it using this equation right here that we saw during the derivation. And so we can sort of rearrange that and say that kcat equals the maximal velocity divided by the total enzyme concentration. And so in other words, kcat is this sort of fundamental property that tells us something about a specific enzyme substrate pair, because we're dividing out and normalizing Vmax essentially by dividing the enzyme concentration there. It has units of product molecules produced per active site per second. And so we often use this inverse second as the unit. Again, this is a first order constant, right? And so it should have units of per second. We often call it the turnover number. And so I can't stress enough that what kcat tells us, right? It is the number of product molecules produced per active site each second. Km, by definition, just like, remember we had P50 or P1/2 from ligand binding, that was the ligand concentration that yielded 50% occupancy. Km is similar. It's the substrate concentration that yields 50% Vmax, or Vmax divided by 2. Now, it's not strictly a dissociation constant. So remember we talked about Kd and P50. Those were true dissociation constants. That's actually what Ks is for enzymes. We're not going to get into Ks too much. But it's not, because there's also kcat involved. Remember, Km was a collection of those three rate constants that we saw during the derivation. And it involves information about catalysis. Kcat's kind of built into Km a little bit. So we can't strictly say that it's a dissociation constant, but it does indeed contain information about binding. K1 and K-1, right, were the formation and the dissociation of the enzyme substrate complex. But we often use Km sort of as a proxy for Ks, sort of giving us information about how well an enzyme and its substrate interact. So for example, a large Km value indicates that it takes a lot of substrate to make the reaction reach that half maximal velocity. If the Km is smaller, on the other hand, it's just the opposite. Remember, that was the same property we saw with Kd and P50 as well. And again, Km is a property of the enzyme substrate pair. So, you change the enzyme, Km will be different. You change the substrate, the Km will be different. It's all about the way the substrate and the enzyme interact. And it's definitely a concentration parameter. One other thing I want to note is, please note that this statement is not true, that Km is not equal to 50% Vmax. Km is the substrate concentration that will give us 50% Vmax. We're going to plug values into the equation in order to determine that. The units on that don't even match up. Units of Km would be concentration, and units of velocity would be concentration per time. So please don't make that mistake. To highlight what Km tells us, let's again look at initial velocity as a function of substrate concentration. And I want to show one enzyme substrate pair that has a very tight binding, right? So something like this. Right, so here's Vmax for that up here somewhere. If I want to look at 50% Vmax, that's about there. And we can sort of estimate where that Km will be. That's going to be the Km for that curve. And let's say I have an enzyme in a substrate, or maybe it's the same enzyme but with a different substrate, and they don't interact quite as tightly. Well, that's going to be a little lazier curve. It's going to shift to the right a little bit. So it might look like this. And maybe it achieves the same Vmax, maybe not, but I'm trying to highlight specifically what's going on with Km here. Well, now this line we need to carry over to here, somewhere around this region, right? So this is the Km for the second curve, and notice that it is larger. It's a larger value than the other Km, indicating that it does not interact as well. It takes a higher substrate concentration in order to achieve half maximal velocity with that second curve. So kcat tells us something specifically about the chemistry. Km has information about binding in it. And so oftentimes we combine those two things to produce this thing called catalytic efficiency. There's actually a second order rate constant. It has second order rate constant units that describe the direct conversion of substrate into product in the presence of the enzymes. But I probably don't put as much effort into that as somebody who's less efficient, right? Maybe somebody can get more done than I do, but maybe they're spending 3 times as much. That's awful. Maybe somebody can output twice the amount of effort. Maybe somebody can have 2 times the output that I do, but if they're spending 5 times the amount of energy or effort to do that time, but it's also, we have to consider the amount of substrate concentration that it takes to achieve that. And that's what. So just to get used to some of these numbers, they tend to be large because we are measuring in per molar per second. And so some of the ones we've heard of before, acetylcholinesterase is in the homework from the last chapter. A couple of these other ones we might encounter here and there, but they tend to have anywhere from below this to thousands up to this range, 10 to the 8th. And an interesting thing we consider, when enzymes have efficiencies approaching 10 to the 8th, we call them catalytically perfect because they're so good at catalyzing the reaction that it's limited only by how the substrates can get to the enzyme. Once the substrate actually does bind, the reaction occurs essentially instantly.